Right, yes, you had a question. Let's close it. Some windows. Okay. When I saw you last, we were dealing with this particular example on the board. I'll read it. A balloon is filled to a pressure of 120 kilopascals on the Earth's surface, where the temperature is 295 Kelvin. The balloon occupies a volume of 0.2 cubic meters. The balloon now rises into the atmosphere where the new air pressure is 50 kilopascals. In other words, it's less. And the temperature, 275 Kelvin, it's dropped by 20 Kelvin. What will the new volume of the gas in the balloon be? Now the formula that you are told to use, let's see if these pens work. P1 V1 over T1 equals P2 V2 all over T2. Let's list what we need for these formulae. P1, V1, T1, P2, V2, T2. Can anyone tell me what is pressure 1? Initial pressure. 120 kPa, kilopascals. What is the initial volume? 0.2 decimeters cubed. What is the temperature initially? Sorry, meters cubed, my apologies. Initial temperature? 295 what? Kelvin. Remember, you don't say degrees. The second pressure, the final pressure, drops down to 50 kilopascals. The new volume, the final volume, we'll put it as a question mark, and the final temperature, it's dropped to 275 K. Right. Now, we need to check that each of those units is in the correct unit. First of all, is pressure in the appropriate unit? What unit can it be in? Any unit, provided the two pressures are in the same unit. Are they? Kilopascals, kilopascals, so that's fine. Right. Volume can be in any unit, provided they are? Well, my answer that I'm going to get here is going to therefore be in meters cubed, so that's fine. Temperature must be in Kelvin. It is in Kelvin, is in Kelvin. Now I can go and do the substitution. Substitute straight into here. P1, 120. Okay, V1, 0.2. T1, 295 equals P2, 50, V2, leave it as V2, second final velocity, volume. And T2 is 275. Right. So therefore we're going to get that V2 equals 120, 0.2, 275. You all agree with that? Over 295, 50. What does V2 work out to be, please? 0.45. What unit? Meters cubed. There's your answer. What do you notice if we look at the question that we originally started with? Okay. What happened to the pressure? What happened to the pressure from when it started to finally up in the upper atmosphere? It dropped. Now, what happens to the volume of a gas if you take the pressure off it, if you reduce its pressure? It expands. Okay. What happened to the temperature? Went from 295 to 275. What happens to the volume of gas if you cool it? It shrinks, contracts. Okay. So you had two factors playing a part here. Pressure was getting smaller, which would have led to it expanding. But temperature was getting less, which would have led to it contracting. Obviously, they won't necessarily cancel each other out. The expansion may outweigh the contraction. Did it in the end? What was the starting volume? 0.2. Final volume? More than twice the size. Okay, so that balloon is expanded. A typical part B to this question would be, explain why meteorological balloons are never filled to full capacity when they are released into the atmosphere. Can anyone tell me why they never filled fully on the Earth before you release them? Because what's going to happen? They probably are going to expand and pop. Okay, so you only half fill them. They go up, and as they go up, they will expand because the pressure gets less and less and less, so that gas will expand. Yes, the temperature does drop, so the gas will also shrink, but the expansion factor outweighs the shrinking factor. All happy with that? Where else would something like this play a part? Car tires, yes. You're going to be riding in hot conditions. You may want to semi-inflate your tires, not inflate them maximally because the gas in the tires will expand, okay, which could cause blowouts. What about your lungs? When you're diving, yes. Okay, so let's take down another example. We'll put it up over there. So this is example 1. Now we're going with example 2. I'm sorry if you can't see this pen too well. A diver at a depth of 50 meters fills his lungs with 2 decimeters cubed of air. At 50 meters, Right, I'll read it in case you can't see it. A diver at a depth of 50 meters fills his lungs with 2 decimeters cubed of air. At 50 meters, the temperature is 270 Kelvin and the pressure is 150 kilopascals. What will the volume of the air in his lungs be at the surface, where the temperature is 300 Kelvin and the air pressure is 100,000 pascals? Right, you all finished? Who's not yet finished? What's the problem? How many pascals in a kilopascals? How many meters in a kilometer? How many grams in a kilogram? Kilo means 1,000. How many bytes in a kilobyte? 1,000. So you divide by 1,000, you times by 10 to the, you're dividing by 1,000, so it's the same as timesing by 10 to the minus 3. So you just write 100,000 times 10 to the minus 3. That straight away does it. Your computer does the thinking for you, your calculator. Yes. No, you can convert them both to kilopascals or both to pascals. It wouldn't make a difference. Right, who can tell me what is P1? 150 kPa. So we're all happy to be, let's see if we can work with another color. It may work better. Let's see if blue works better. 150 kPa. V1. What is volume 1? Initial volume? 2 decimeters cubed. Right. T1. P2. 100,000 pascals. We can't work like that, so we say times 10 to the minus 3, and that brings it to kilopascals. Just leave it like that. That's fine. Okay. V2 is question mark, and T2 is 300 Kelvin. Okay, let's substitute into our formula. P1, 150. V1, 2. T1, 270. P2, 100,000 times 10 to the minus 3 times V2 over 300. When you do that, V2 comes out to be what? 3,33 recurring decimeters cubed. Right. What's the problem? If you took a deep breath from your scuba tanks and up to the top, 50 meters up. You were diving 50 meters below the surface. You took a deep breath and you went up to the top to the surface. What would happen to the air in your lungs? How much air would you fill into your lungs down at 50 meters? 2 decimeters cubed. How much space would that same air occupy at the surface? 3,33. In other words, it's increased by 50%. Can your lungs increase by 50%? Yes or no? No. What's going to happen to your lungs? They're going to pop. Okay? So you would have to breathe out as you go up. If you don't, your lungs will burst. Because that air expands. And there's only so much expanding that your lungs can do. However, your lungs are one thing. You can breathe that air out as you go up. If you don't, you'll know all about it. You'll have to breathe out. It'll be so painful. But where can't you get rid of the air? In your blood. There's air dissolved in your blood. Certainly oxygen dissolved in your blood. And that's also getting bigger. So what does that oxygen start doing? Forming bubbles in your blood. And that's what's going to cause problems. You'll have a heart attack. You'll have a brain stroke. Because blood can't get through the fine blood vessels if they're bubbles. They clog. They stop. A bubble acts just like a clot. It stops the blood from flowing, and that can kill you. So that's what's the disease called? Not the disease, not a disease, but what is this? The effects of this called when you rise up too quickly from deep pressure, high pressure to low pressure. The bends. Okay, I don't know where the name came from, but it's called the bends. Right. How do they sort it out if you do end up doing this? You end up with bubbles of air in your lungs. They can do that, yes. Doesn't help. You normally would go up in stages, give the air in your blood a chance to regulate itself up, and so forth and so forth. You've got to spend a certain amount of time at every stage. But what say you don't? They put you into a compression chamber, like a big steel tank, and they build the pressure up again to the same pressure that you would have been down at 50 meters. And they leave you there for a day or two. And then they slowly reduce the pressure and bring it back to, but hopefully you won't have had any brain damage by then or other tissue damage. Right. So these are the type of calculations that we're doing with gases. Quite actual, reasonable calculations. We've got 4 minutes left. Let's give you one example for homework. Yes.
Increases to 270
Ah, 280, my apologies. That I'm going to teach you. We'll do that on Wednesday. The volume of a tire is fixed. In other words, the tire doesn't expand and get bigger or smaller. It's a fixed size. Tires have got steel inside them to prevent them from expanding. When inflated at 273 Kelvin, the pressure is 2 bars. After driving for 20 kilometers, the temperature increases to 280 Kelvin. What will the new pressure be? Right, you need to finish that for tomorrow. Please don't forget that tomorrow we do have an extra lesson.